to give you just a quick. I'm jumping around here. I appreciate it's slightly annoying, but so what I'm going to do now is I'm going to basically talk very briefly about the parallel traffic modeling. Then we'll do some real MPI, and then by about before lunch we'll hopefully log on and be able to run programs on Archer 2. But I'm just going to. It is a useful reference point, the traffic modeling. So I'll spend about 10 minutes going over that, and then we'll do. Then we'll talk about MPI programs and MPI and Archer 2. So what if I can find the right. So what I am, the exercise, I will just, I'm not very good with multiple windows. It's not really my forte. That's the exercise sheet, but the lecture I'm going to go, which actually covers the solution is, I'll put that in the chat as well. This is the solution. So very briefly, I will just say what I wanted you to think. But I appreciate there's not a lot of time in this condensed course to apologies for all the okay. So the you should see the so this is the exercise sheet which I talked about, but basically on the typo. Okay, really, I really want to talk about the message passing implementation. Okay, how would you implement your parallel scheme using a message passing program model on a distributed memory parallel machine? And my diagram of the three people with their traffic models kind of illustrated this. But how would you divide the data amongst the different processes? When is communications required? I've talked about that a bit, but we need to come back to that. And how would you calculate the velocity each time? What we want to do is we want to compute the average velocity of the cars. We need to know how many cars have moved. And of course, each person only knows how many cars moved on their own road, not the global road. And then in terms of the pseudocode, I want you to consider what happens whether you send it asynchronously or synchronously. And that is a slightly subtle point, which I'll hopefully illustrate. But what I was going to do now is I've just got this little lecture, which will go over, just talk about the issues of solving that problem. And so we should be able to get that going if I can get my Windows machine to come alive. Has its moments. Okay, so I'm going to very briefly go over the solution here, and I've talked about quite a few of the things already, but it's worth talking about. And please, if you have any questions, put them in the chat. So the update rules are the important part of the traffic simulation is that the update rule, the state of a new cell depends on the state of your own cell, but the state of your nearest neighbors in both directions. So that's the fundamental thing. To update a cell, you need to know what the value of that cell is. Does it have a car or doesn't it? And you also need to know the value of the cell before and above. And you can draw that as a state table, whereas if these are the values of all the cells, if currently we have a gap, a car, and a gap, then it will end up being, oops, sorry. It will be you can do it as a kind of a table like this. In this situation, if the current cell is full and the one upstairs is full, it stays full, it stays full. In these cases, it goes empty because it moves away. And here, if the current cell is empty, if there's one behind you, you become full. But I think maybe the pseudocode is more useful to do that. But it's the other ways of thinking about it, and you can talk about it at the state table. That's really just the same. That's just the same information presented in a different way. So this is my pseudocode, okay? And I think the important point is that to update a cell, okay, to update, you need to know the values of old of I plus 1, old of I minus 1. So to update the cell I, you need the cell on I plus 1 and I minus 1. And of course, that could be on a different process. That could be somebody else's road, okay? Because you split the road up into sections, because you're looking up the road and down the road, at the edges of your road, that's going to be looking to your neighbor and to your neighbor up the way and down the way. So in a parallel program, looking at the next or the previous cell incurs communication. And so what parallelization strategy people might have is, well, I'm going to do a very simple problem here. I've got a road of length 8, and I'm going to consider 2 processes. That's way smaller than you'd really do, but it's just so I can draw it. One parallelization strategy people might do is, well, let's broadcast. Okay, so we've got a road here. Let's broadcast the road to 2 processes. So each process 1 and process 2, has a copy of the entire road. Okay. And then what we say is, if I'm process 1, I update the first half of the road. If I'm process 2, I update the second half of the road. So we split the calculation that way. And then when we update our road, we then have to globally resynchronize all the data after each move. That means that when I've updated the road, only a part of my road is up to date, and then I have to do a resynchronization to get all the state of the other road from all the other processes. So this is called a replicated data strategy. Every process stores the entire state of the calculation. Now, this is not a good strategy for parallel programming in general for 2 reasons. Can anyone think of what? So what we're going to do is we're going to say that everybody's going to have a copy of the entire road, and you just update the portion that you're responsible for, and then you gather the data from all the other pieces of the road that other people have. Okay. Why is this not a good strategy in general? It's a strategy people used in the early days. So most people don't get that one. You're absolutely right. The memory cost is absolutely right. So, for example, Archer 2 has almost 1 million processes, each with hundreds of gigabytes. So that's, I don't know how many terabytes of data Archer 2 has. This would be saying you can't run a calculation which is the entire state of the calculation has to be able to be stored on a single processor. So you'd be saying Archer 2 has terabytes of memory, but you can't run a simulation which is more than 2 gigabytes long, and that's clearly crazy. So clearly, I often say the only reason that people do parallel computing is that the only reason we use parallel computing is that we want to access multiple processors for computation, but actually it allows us access to the memory. So yes, memory is bad, but also I saw that Christoph said also lots of data. Also, it's a terrible strategy in terms of communication, because this global resynchronization means that everyone has to talk to everyone, and it doesn't scale. So it doesn't scale in terms of memory consumption and in terms of parallelization. You're doing way too much communication. What you want to do is you want to say, I know what the communications pattern is. I know that each process only needs to communicate with 2 other processes, and so I will do that. Okay. So what's better to do is to do a distributed data strategy. So what we do here is we don't broadcast the data, we scatter the data. So imagine, we do have the state of the road on a single process. We scatter the data, okay? So it's a distributed data strategy, okay? So this is just like I draw the diagram of the people with their chessboards. The first process only has 4 elements, the second process only has 4, okay? And the important point is the internal cells can be updated independently. You can update all the interior cells, but it's updating the edge cells, okay? Updating the edge cells is the problem. You have to communicate with your neighboring processes to update the edge cells. And at the end of each move, and at the end of each iteration, you will have to sum the local number of moves on each process to obtain the total number of moves at each iteration. Okay. And so you split the calculation between two processes. Each process must know which part of the roadway it's updating. But at the completion of each iteration, you have to synchronize and obtain the total number of moves. So obviously, this is a distributed data strategy, and this is almost universally what is used in real parallel programs. The question is, how are we going to do the communication? Well, parallelization. First of all, load balance means making sure that all the processes have the same work to do. Well, this is a very simple problem. And so, for example, if we have a road of length n on p processes, we just give each person a road of size n over p. So, for example, when I had a road of length 15 and 3 processes, each process with a load of length 5. There are situations where it's not that simple, but for simple problems, it's that. For each piece, as I said, the rule for cell I depends on cells I minus 1 and I plus 1. And so most of your cells, the interior cells, if you have n over p, the n over p minus 2 interior cells can be updated independently in parallel. Okay, it's only the edge cells that are updated by other processes. And actually, this is typical of many scientific and technical calculations, often those which come about from discretizing partial differential equations. You have an update rule where a cell depends on its nearest neighbors. So if you're in a large amount of the array or the domain, most of that can be updated. You just need to communicate with your neighbors to get the boundary information. So this communication is required at 2 stages to get the value of the edge cells from other processors and to produce a global sum of the number of cars that move. And the way we do that, so this is what we want to do. We want to start off with that situation and end up with this situation, is we add halos to the data. So what we do is each process gets a road of length 4, but we extend that road to have these, often people call them halo cells or ghost cells. And what they're used for is they store the data from your neighboring processes. So rather than saying every time you need to get data from another process, you ask for it, what you do is you say, typically you say, I'm going to gather all the data I need so that I can do the next iteration myself. So that means I need to know what's going on to the left of me to the right. So basically, you have to you grab the data from your neighboring processes and stick it into the edges of your array. So you make a local array bigger and you fill in the data with the data from the other processes. So what you have to do, you have to copy the data, or this involves message passing, that value has to go into there, that value has to go into there, that value has to go into there, and that value goes into there. Once you've done this communication phase, you can now do your computation independently because you have copies of all the data you need. You can update the interior cells. You get the right answer, and then in the next phase, you have to update the halos again because those data has changed. So this trick, what we tend to do is that we do all the communication we need in one phase. So we have a separate communication phase. So these calculations typically alternate between communication and computation. And there is a subtlety here to do with the synchronous versus asynchronous send, but I'll cover that in more detail later on. So I don't really want to go into it in any detail here. So are there any questions about that? Why I think this is a useful example is it illustrates standard communication patterns. It illustrates why a scatter might be useful because you have the road stored. You might read the data from a file. So you have the road stored on one process who then needs to distribute the other, and they would scatter that data. Use point-to-point message passing sends and receives for swapping the halo data. But then at the end of each iteration, you need to do a reduction operation, a global reduction, where each process says, well, I had 3 moves, you had 4, you had 7, you add them all together. So absolutely, a similar strategy is typically done with a 2D grid. So yes, or in 3D, what people would typically do is 6-way movement, up, down, forward, backward, left, right. So this generalized, now, not all calculations are this simple, but a large class of calculations, those coming from partial differential equations, often fit this strategy. So this technique of halo swapping generalizes to 2D and 3D. And in fact, the comms overhead isn't too bad because it's a surface to volume effect. Yeah. If you have an L by L by L grid, yeah. So let's say in 3D, yeah. In 3D, the computation grows as L times L times L, yeah. But the communication, the surface to volume effect, is L squared. And so if you have a big enough value of L, so you need large problems, but if you have a big enough value of L, then the computation will dominate the communication. That's a very good point. Does that answer your question? So it does generalize, and it works because of this surface to volume effect, that your computation hopefully is always significantly bigger than the communication. If your communication and your grew linearly with the computation, you would not be able to. Okay, so we're now, as I said, because of my slight faux pas earlier on, we're going to be able to. I will now put it as I've requested. So this is the next lecture, which I inadvertently started. So I do apologize for that faux pas. I was thrown by the audiovisual issues. It's my excuse. So I can skip all the stuff we've done before. We're now going to talk. We're going to actually see some actual code. Okay, so there where are we? L. So I've talked about the fact we've done this lecture before. I inadvertently gave the first few slides of this lecture before. MPI has been a long range effort going on about 30 years. Library, not a language. There's no such thing as a compiler, although it is slightly confusing in that respect. And we talked about source code portability and the and heterogeneous architectures. So the first thing you have to do, because it's a library, you have to include a header file. Okay. In C or C++, now if you're a C++ programmer, I'll tell you ahead of the way. MPI is not a C++ library. You can call MPI from C++, but MPI is a C library. Okay, so there's no object orientation or whatever. So the interface between C++ and MPI is perfectly well defined, but to C++, MPI looks like a C library. Okay, but in C or C++, you hash include MPI.h. In Fortran 77, you include MPIF.h. I hope nobody does that anymore. It's very old-fashioned. In Fortran 90, you do use MPI. There are significant differences in the 2008 interface. They're cosmetic, but significantly cosmetic, and I will cover them later. I will cover them with a specific example. You do use MPI everywhere, but in all the Fortran examples I will use the Fortran 90 interface because that is the one which is still most commonly used. Because MPI is a library, it's a bunch of function calls. All of them have a prescribed format where you do error in C, you do error equals MPI. So all the function calls have capital MPI, then lowercase x, and you pass a bunch of parameters. Every MPI routine returns an error code, but in fact, people often ignore the error code, and C being C, you're allowed to ignore it. The reason that people ignore the error code, although you shouldn't, is that by default, MPI crashes whenever it discovers an error. So you will never get an error code back in MPI by default because it will crash and burn. Now, you can change that behavior. You ought to check the error code, but people tend not to. In Fortran, okay, in the Fortran 90 interface, the error code is an extra argument. So in Fortran, the capitalization is irrelevant because it's Fortran. You call the subroutine and you have to specify an error code. Now, if you're using the 2008 version, the error code is optional. But if you're not, you have to specify it, even if you never look at it. It's because in Fortran 2008, you have you can overload functions which have different numbers of parameters, but in Fortran 90 you can't. So, but that's so they're just function calls, okay? So this is a slightly obscures it, but often MPI has its own internal data structure. We'll see that MPI is able to have concepts like groups of processes. You might have lots of processes and you might have groups of them. Now, MPI has structures called, they're typically called handles. What I mean by this is that basically, imagine you're opening a file. In Fortran, you open a unit number. In C, you open a file pointer, okay? Now, those things have an enormous amount of information stored somewhere. You just need to remember them. And MPI calls these handles, okay? So you'll have a handle, and when we get explicit ones, will become more obvious to refer to these. In C, the handles are all defined type defs. So they're different types. Okay, we'll come back to that. In Fortran 90, all the handles are integers, which is slightly awkward, and that's because when MPI was defined way back, Fortran did not have user-defined types, structures, or whatever. In Fortran 2008, the handles are user-defined types as they are for C, but we'll only present the Fortran 90 interface here, but I will give you enough information to use the Fortran 2008 interface, because so I'll give you some specific examples. So for example, okay, so because it's a library call, you have to initialize it, okay? One of the problems, one of the nasty things about, there are a few nasty things about MPI. One is that the initialization routine in C looks very complex. This is not what this is the prototype, okay? MPI int star argc cast double star argv. What this is saying is you have to you're supposed to pass a pointer to argc and a pointer to argv to MPI init. Now, that I'll explain why that is later on. Fortran, it's much simpler. You do call MPI init IARA, integer IARA, okay? Now, I'll give you an example which explains these things. This must be the first MPI procedure call, but as I think it was Andre or Alexei? Apologies, I can't. I've forgotten your name. Anyway, somebody said that MPI programs are parallel right from the start, unlike OpenMP, and that's absolutely true here. This MPI init routine does not launch the parallel program. Okay, the parallel program is launched by the launcher routine, and we'll see that when we do real examples that that the MPI program is parallel from the start. Okay, but it must be the first MPI procedure called. However, multiple processes are already running before MPI init. So when you call the launcher program, if I run an MPI program on 4 processes, the launcher program launches 1, 2, 3, 4 processes. All the MPI init does is get them to communicate with each other. But it's much more easy. We see a specific example. Okay, so what you're supposed to do for MPI in C is you have int main, int argc, char star argv. These are the command line arguments, how many arguments there are, what they are, and you're supposed to pass a pointer to argc and a pointer to argv to MPI init. However, you might say, I don't have any command line arguments. So actually, most people do this, okay? Most large-scale scientific and technical programs don't take command line arguments. You pass in the parameters through a file. And so typically, actually, most MPI programs in C begin int main void, MPI init null null. Okay, that is how you're allowed to pass null here as a null pointer, okay? In Fortran, you do program my MPI program, integer IARA, call MPI init, okay? So is that clear? Okay, so most C programs begin like this, and you also have had to clearly included the error further up. You had to include MPI.h or use MPI. So one of the fundamental concepts in MPI is a communicator. In MPI, all communications takes place within a communicator. Now, communicators are fundamentally groups of processes, and we'll talk later how to create your own groups of processes. So you might want to say, I have 8 processes. I want the even processes to be in their own group and the odd processes to be in their other group. You can do that, but for the moment, a communicator is a communications world. It defines the scope of all communications, And there's a predefined communicator called MPI-COM world. It's predefined. So whenever you see an MPI function or subroutine that needs a communicator, just pass MPI-COM world for the moment. We will see later how to exploit communicators for more general purposes, but whenever you see a communicator required as an argument, you can pass MPI-COM world. So rank. The fundamental thing you need to know to write a working program is to be able to differentiate yourself from your other processes. How do you identify different processes in the communicator? I've said that, okay, what I'm saying here is if I run an MPI program on 8 processes, those 8 processes are all part of the communicator called MPI-COM world. They're all a member of MPI-COM world. And I've numbered them 0, 1, 2, sorry, I've done 7 here, apologies. I've numbered them 0 to 6 here. That's what MPI does. If you run N processes or P processes, they will be numbered 0 to P minus 1. However, you have to find that number out. How do you find that number out? There's a routine called MPI-COM rank, which says you give it a communicator and it gives you back a rank. MPI-COM rank says, what is my rank in this communicator? Okay. Now, so you have to pass it a communicator, and in C that is of type MPI-COM. That's one of these handles, these type defs. Okay, and you get back the rank. In Fortran, you call MPI-COM. How is the Fortran routine different? Well, first of all, you have this extra IARA variable, but also the communicator is just an integer. So as I said, in the Fortran 90 interface, all these concepts, these things like communicators, and we'll see other things, are in Fortran just integers, whereas in C, they're types, and this is of type MPI-COM. So the rank isn't the physical processor number. It's an internal, it's MPI's logical numbering of the product. So we will see that you can ask for your MPI-COM rank says, what is my rank within this communicator? By far the most important rank is your rank in COM world, because that is guaranteed to be unique. So it's almost impossible to write a useful MPI program without very early on saying, what is my rank in COM world? And that gives you your unique identifier. Am I 0, 1, 2, 3, 4? Once you know that, you can do lots of stuff. But without that, you can hardly do anything. So your classical Hello World program in C is int rank, MPI-COM rank, MPI-COM world, give me back my rank, and print hello from rank whatever. In Fortran, it's called MPI-COM rank, MPI-COM world, which again is these are defined in the header file somewhere, rank IARA. Okay, so these look very similar. It just happens in C, this is a variable of type MPI-COM, and in Fortran, it's a variable of type integer. Okay, so that's your standard Hello World program, MPI init, MPI-COM rank on MPI-COM world. Okay, is that clear how that's going to work? So when you launch an MPI program, all the processes boot up. Okay, they come alive, but they don't know who they are. So the first thing you have to do is say, who am I? You know, I've just come alive. What's my name? Am I rank 7, rank 53, or whatever? The other thing you need to know is how many there are, because when you write MPI programs, you write them for a general number of processes. So when you launch the program, if you might say, right, what's my rank? I'm rank 7. By default, you don't even know how many processes there are. So what MPI-COM size says, how big is a communicator? How many processes are there in a communicator? Now, if you ask, because MPI-COM world contains everybody, if you say how many processes are there in MPI-COM world, that's the same thing as asking how many processes are there in total. And so the two things you do, three things, MPI init, MPI-COM rank, MPI-COM world, MPI-COM size, MPI-COM world. So MPI-COM size tells you how big a communicator is. So by definition, everyone gets back the same size, but everyone gets back a different rank. So having asked who you are and how many of there are you can then do useful things. And they're important numbers because if you think about the traffic model, you need to know who you are to know who your neighbors are. If I'm rank 5, my neighbors are 6 and 4. Okay, but also I need to know the size because I need to say, well, the total road is 15, but what's my chunk? Well, if there's 3 of us, it's 50 over 3 is 5. So you know your rank and the size are fundamental to writing a correct parallel program. To exit MPI, you call MPI finalize. It must be the last MPI procedure called. But as somebody mentioned before, the model is MPI init, you run your program for 10 hours, MPI finalize, quit. It's not like OpenMP where you do begin parallel, end parallel, begin parallel, end parallel. MPI programs are parallel all the time. You initialize MPI at the start. As I said, you run for 10 hours and you finalize and then you go away. Okay, you cannot reinitialize MPI having finalized it, but you need to call MPI finalized so that the library can do tidy up. So you do need to call MPI finalized. MPI tries to be quite removed from the hardware. It talks about processes. It doesn't talk about physical processors, but often it's very useful to know things like, for example, if you go back to the example I had, I talked about a machine where you had 5 computers, each with 4 nodes, with 4 processors, 5 quad-core laptops. You want to run 20 processors on that. You would like to be confident that you've got 4 processors on each node, 4 processors on each computer, not 20 processors on the first computer and none on the others. And so it's often quite comforting to say, look, what is the name of the computer, the name of the node that I am running on? Okay. Now, for historical reason, MPI calls that MPI get processor name. That's because when MPI was invented, a computer had a single processor. Now you would call it MPI get node name or MPI get computer name. But anyway, it's often useful to do the functions like this. You declare a string of size MPI max processor name, and you call MPI get processor name of the processor name, and you get back the name length, which isn't relevant, particularly in C. Or in Fortran, call MPI get processor name, proc name namelane error, where this is of type character start MPI max processor name. This is sometimes quite useful to do because it just gives you confidence that your processes are laid out across the nodes, across the physical machines, as you would expect. So summary, I've covered some basic MPI calls. I've not talked about any message passing. I've not told you send and receive, but we could still write some relatively useful programs. You know, if, for example, I had 1,000 files to process, I could run a program on 1,000 processes, and I could say, if I'm rank 0, process file 0. If I'm rank 9, process file 9. A task kind of independent jobs. But we need to compile and launch parallel jobs. And this is not, MPI doesn't really specify this. And I'm going to give you some machine-specific details on Archer 2, and then we'll get back on and we'll do an exercise. Are there any questions about that? We're just going to do a Hello World program on Archer 2, but okay, oops. So this lecture actually, so the next lecture is now this. So so there are 2 ways you can do it. One is so MPI is a C library. MPI is written in C by C programs. Okay, so and then used by Fortran programmers. So there are 2 ways you can do it. One is you can one is the Fortran integer can store the address of the C object. So you just store the address, or you just have a lookup table. So internally, the library contains a lookup table. So it stores all the objects in a line. So and it just counts. It says, oh, that's 5, so it must be the 5th one. Does that make sense? You're right. There's some mapping under the hood. It's fundamentally a C library. So there's a bit of glue code to interface between C and Fortran. But under the hood, it will just have a lookup table or something like that. Yeah, it's not defined, but does that make sense? There's different ways you can do it. So, okay, sorry, I'm now, yeah, but it is important. I think it is useful to realize that fundamentally it is a C library because you would never write a system library like MPI in Fortran. So this covers a number of machines, including our system Cirrus, which I'm not going to. So I'm going to skip some of these slides because this is a generic. So access, you just SSH into Archer 2. You can use SSH from anywhere. Linux is straightforward. Mac terminal command line is useful, but if you want to display graphics, we won't be using graphics till a week tomorrow. But if you do want to do graphics on your Mac, you'll have to enable something like Xcort. On Windows, it's much easier to use MobaXterm. MobaXterm is really useful. So actually, that would be an interesting question, which I should have asked at the start. So give me a second. I'm going to ask you a question. Could people tell me if they're using like Mac, Windows, or Linux? Let's wait for a few more responses to come in, but so mostly Linux on Mac and Windows. So definitely Mac is easy, Linux is easy. Windows, you should definitely use MobaXterm. I'm a fan of MobaXterm. It solves a lot of problems. So the only issue we have, not the only issue, but accessing our systems is slightly harder than you'd expect, because there was a global security exploit a year and a half ago to do with SSH keys, which but interrupted the service of a lot of HPC systems worldwide. And so we require you to have SSH keys and stuff uploaded, and it's a bit complicated. That's what we'll probably spend the first session sorting out. This gives you access to a login node. Oops. There's a few login nodes. Login nodes are shared by all users, but many hundreds of compute nodes are accessed exclusively by the Slurm and BAT system. So on Archer 2, MPI programs only run on the compute nodes. So on Archer 2, it's unusual actually. You cannot run an MPI program on the login node. Okay, you cannot run an MPI on the login node. But I will give you a separate document on how to script this. But you cannot run an MPI on the login node. Okay. Whoops. So this is not. So a typical HPC system layout, you log into the login nodes. There are some compute nodes. Well, there's a few of these, and there's thousands of these. They share disk so that you can share data between them. But the only way you access them, you never log on to the compute nodes. You use a batch system, and that we use something called Slurm, which is completely standard. There is I don't provide much code on this course. I do actually provide the solutions if you look simple solutions, but it is useful to write programs from scratch just to see that it's not magic. But I do provide something called mpptemplates.tar, and I'll unpack it. I'll go through how to do this. Cirrus environment isn't relevant. Okay, so sorry, I've done something really stupid here. I apologize, but I have. I'm going to have to re-upload this lecture. I have. I have hidden the slides. The last time I gave this lecture was for. I'm going to have to re-upload this lecture. Apologies for that. Last time I gave this lecture was for Cirrus, and so I have stupidly not unhidden these. And so I have to reconfigure this lecture for the. Okay, so I apologize for that. I will re-upload this. Right. So compiling MPI programs on Archer 2. Normally, the MPI is accessed via a compiler wrapper called MPI-CC or MPI. On Archer 2, because it's a dedicated parallel machine, they'll say, well, nobody wants to compile a serial program. So the default, what look like serial compilers, CC, capital CC, and FTN, are actually the parallel MPI wrappers. I said before, there's nothing magic about these MPI compilers. They're simply wrappers which automatically include various libraries. And actual compilation is done by the standard, by default, the Cray compilers, Cray 4-channel Clang. I've given you simple make files, which you can use if you want, but it's really very simple. I'll show you how to do that. Archer 2 idiosyncrasies. It's not possible to run MPI programs directly on the login nodes. There can be a substantial delay in the batch queues. There is a short queue, but I've given you dedicated queues. I'll show you how to use them. The really important thing is you cannot run from the home file system. When you log in, you're in the home file system, but you cannot run parallel jobs from the home file system. So your working directory is home/project/project username. So I recommend that as soon as you log in, you change your /work directory. Okay, and the crib sheet covers how to do that. Okay, so when you log in, you're on /home, but you should go directly to /work. On the back end, we run via a batch system on Slurm, and there is a simple, there's a very, very simple script called archer2mpi.job. It says here it's set up to run a program called hello in the short queue. It's actually set up to run a program called hello in the reserved queue for today. So I'll show you how to do that. And by default, it runs on 4 processes. And I will show you, the easiest thing to do is for me to show you how to do that. You cannot run on the Archer 2 login nodes. However, there is a way of sort of running interactively, and you can do an S run. So yeah, it's up to you what you want to do. I'll show you how to do these 2 things live. So again, C++ interface, MPI is not an OO interface, but it can be called from C++. Originally, it had different function calls. Originally, they supported a kind of OO interface where the object was the object was the communicator, and the functions were methods. But that has been deprecated now, so you must cross-call to C. Documentation, there's a standard available. There is actually a version, there's lots of versions, but 3.1 is a reasonable one there. It's available online and the standard place. If you want a book, this is a very good book using MPI, written by some of the people who designed MPI in the start. If you're at Edinburgh, this is available on the Edinburgh University Library. I asked for it to be available electronically. Otherwise, you'll need to buy a copy or ask your local library to get a copy. So exercise 1 is the minimal MPI program. And what I'm going to do is to just run through how to get up and running. And so what we're going to do is I will put up the URLs. What you need now is you need the exercise sheet, which is, we use one exercise sheet for almost all the so I put these in the chat. Useful code is there. Okay. The exercise sheet is there, and the code sheet running on Archer 2 is there. What I will do is I will I will basically well, I will go through the crib sheet, but I will do it online. So if you, I would recommend that you have a copy of the, before we look at the exercise sheet, I would look at a copy of the crib sheet. So I'll get that up. Okay, and what I need to do is So I share the correct thing and then we can get up and running. Okay, so you should be able to see my terminal there. Okay, so what we need to do is we need to first log on to Archer 2. So I'm going to do my login is TA57 TA057DSH. I've just made up at login.archer2.ac.uk. Okay. If it's the first time you've logged on, there will be some complicated process of resetting your password. But if not, I've already logged on. I'm on. Okay. So people try and look if we could now, if people would log into Archer 2, okay. So I would useful to, so if people are having problems, this is where we can help and maybe go to a breakout room. I appreciate it can be slightly tricky and not immediately, but we can screen share, and that's the easiest way to solve these. So what I'll actually do is I'll run through what we're going to do here, and then if you do have problems, we've got we've got 3/4 an hour of an exercise, and we can sort out any individual problems during that. Okay. What I need to do now is to get the I've got some old files here, so I'll remove them. Okay. So I'm in /home. I need to go to /work /TA057 /TA057, and then your username, which to me is TA057DSH. Okay. So this is all explained in the crib sheet. I've actually got all the stuff here, so I'll get rid of that. Okay. Now you need to get that crib sheet, that template across. The easiest way is just to wget it from Archer 2. So actually, by far the easiest way, you can SCP it and all this stuff, but what I tend to do is just use wget. So that is the crib sheet, and now I have it. Okay. I unpack it, and I get some stuff, and I'll go into there. If I see the MPP templates, then I can see I've got, and what I can do is I can compile. So I have a hello.c. Let's just do cat hello.c. It does nothing except the hello.c is really, really trivial. It just does include MPI, but it just prints, it does nothing other than print hello world. The exercise in the exercise sheet is to put in MPI-COM rank, MPI-COM size in here, but this is our default program just for the moment. Okay, I can compile it. Files it, or I can use the make file. Does the same thing. Okay, it's not, that's what it does. Okay, so now I have a code. You could do the same with the Fortran, but I now have an executable called hello. Okay, so I've compiled that, and I need to run it. And if I realize now we want to, my Emacs isn't set up correctly. If we look at the batch file, this is set up. It's all kind of magic, but what it's set up is to say it's set up to run on one node and 4 tasks per node. So it's going to run an MPI program on four processes, and it's just set up to magically run in today's reservation. Okay, so this is all set up by magic, but the actual run command is at the bottom. This is the magic to run the program called hello. This is all hints to the batch system, which we can discuss later. But the important point is srun is the Slurm command for running a parallel program, and you run hello. Okay, so what we actually do is we do sbatch archer2mpi.job. I can look at whether my job is running, new TA057DH, my user, and it's running. It should run eventually. Run, and you'll see you get an output file hello.out, And if we look at that, that did what we expect. It did hello world 4 times, okay? I could do the same with the Fortran, and I could do the same. The Fortran is just this, okay? The same thing. So that allows you to compile and run the program. The other thing you can do if you look at the template is you can run interactively with this magic command here. It's in this crib sheet. So there's a mistake in the crib sheet because this has changed since the last time I ran this course. So apologies for that. I will update it. This is wrong in the crib sheet. I will fix it. I will fix that. This is a way of running semi-interactively. Basically, it blocks and waits and then runs on the command line, and it will run eventually. Hello world. It's up to you if you want to S-batch the batch script and look at the log file, or S-run interactively. I will fix that script. Apologies that it's I'll fix that live. Are there any questions on that? So actually, I'm just fixing this sheet. Give me half a second just to get this going. Sorry about this. It's my mistake. I think I've updated the sheet now, so apologies. I'll get back online. Okay, so what I was trying to say is that basically you should follow the crib sheet. The crib sheet. So sorry. So first of all, we had a question from Christoph. Yeah, Christoph.
Can you hear me?
Yeah.
Okay. The question is about the work directory, because I'm getting the warning that I'm not using the work directory when I specify srun, but I cannot write on work. So
no, but the directory exists already. So what's your username?
C. Welfler.
Can you type it into the
Yeah, sorry.
Okay, so you should just be able to go. Can you see? You should be able to go to ls-work/ta057/ta057/ Oh,
okay. I did not know the TA subfolders.
So that's weird though. Why is that?
Maybe it's some old residue, because I took a course last year for modern C++, and I had an article.
So okay, so you haven't applied for a new account?
Yes, probably.
So you
I just try to use the old one.
You will be able to run from the old one. I can show you how to do that. There's no problem. You'll be able to run from the old one. There's not a problem. Okay. You just won't be able to use the reservation, but you'll be able to run. Yeah. So we can fix that. Probably best if we go into a breakout session. But so Monica, apologies. The reason I went through it very quickly is the hope was that you can just follow that crib sheet. Yes, see the crib sheet. The crib sheet should just has these instructions in it, and I'll share that on the screen here. Okay, give me a second. The crib sheet, which you should have access to, should just give you, yeah, just follow I just did exactly what was on the crib sheet. I just wanted to check it worked, yeah. But you know, you should just be able to follow the instructions on the crib sheet and get up and running. Is that okay? So is that okay? I went through it very quickly just because, but I can't. Yeah, so if I could have shown two screens at once, but that's the idea. I just wanted to go through very quickly what I did there. That should work. Okay. So I will just, Christoph, we basically just, I'll do a very quick. So my colleague Mark is around at the moment to take questions as well, but I'll just break off into a breakout with Christoph, and we'll just show you the couple of tweaks you have to do to get the exercise work. So I will disappear for a second, but I will be. So before I disappear, the idea is you follow the crib sheet. That should get you on, and you should be able to compile and run this simple Hello World program. Okay. After that, what you want to do is to follow the actual exercise sheet, which is a bit more interesting, and that I get the exercise sheet. I'll just show you. Okay, I'll share that. The exercise sheet. Yeah, I've got Cirrus here, but I'll meet my Archer 2 here. And then, you know, I want you to modify your product. Each process has both its rank and the total number of processes. Modify your product in a single controller process for M0. What happens if you omit the final MPI procedure call? And there's some extra exercises here. Yeah. So there's a bunch of stuff there. But the main thing is just to put in MPI com rank and MPI com size and MPI com rank calls to show that you can actually run some actual MPI. Okay. So you should be following that. So hopefully the crib sheet will allow you to get up and running the simple supply program, and then you'll do the Hello World exercise there.